Okay, so we have discussed about symbol table yesterday, but let me discuss it again. So what is the symbol table is, as you know that whenever you write or whenever you define the data in this way, in assembly language, that means one by one, then the assembler, what actually the assembler does is they allocate the memory location serially, right? So that you can find the specific variable data easily. Okay. So what is the symbol table then? Symbol table is there is a after defining this type of data, the assembler is actually make a table, and there is a two column. One column, first column is the variable name, and the second column is the offset value. And we know that what is the offset value is. Offset value is actually the starting point of that variable into the memory. Starting point of that variable into the memory by using a number. Okay, so let's say for example in this case value is a variable. We have a two we have defined it dw, that means it's two words. Okay, so that means first byte and second byte is actually for the value. All right, so whenever the sum, we have another variable, next variable is called sum. That means the sum variable will start from third position. So if we start from 0, that means see it start from the 0, that means the sum will start from the third position. That means the offset value will be 2, because the value of the variable value actually has 2 bytes. That means first 2 bytes are occupied by this value variable. Then sum will have 4 bytes, because dd means double word. Double word means 4 byte. So we know that the sum is actually occupied 4 bytes. That's why when the marks variable will start, that means previously value variable occupied 2 byte, and then some variable occupied 4 bytes. So altogether 2 plus 4 is 6. That's why marks will start from 6 position. Okay, 6 actually 7th position, but it was starting from 0. That's why we write it 6. Okay, the same way we also have the message value. Message, this one is 26. Why it is 26? Because this one, as you can see, is actually an array where we have 10 elements, and each of the elements has 2 bytes, because it is dw. That means 2 byte. So one word 2 bytes. So that's why 10 times 2, 20. So previously it was 6. Now plus 20 is 26. And how the character 1, what will be the starting point of character 1? It is 40. How it is 40? Because we know that the previous one, the message, this one, how many we have? We actually define, as you can see, as you know, that if there is an inverted comma, that means in between this inverted comma, everything is a character, including the space. That means each of the character occupy 1 byte. As you can see, this is the db, and this is called multiple declaration. We know what is multiple declaration, right? That means how we can define multiple data in a single line. That is a multiple definition. So that means each of the character, including the space, is one byte. That means we have 1 2 3 4 5 6 7 8 9 10 11 12 13 bytes, 13 bytes for that, because we have 13 characters here. And then comma 0, that means we have another variable, so altogether 14. That's why 26 plus 14 is 40. That's how we can have the symbol table. Make sure you know this explanation and calculation very well, because it's a very, very good question for your exam in the final. Okay, so now let's start to the 4.3, which is a new topic for us, which we call addressing mode. Okay, what is an addressing mode is, we know that whenever you do any operation, any kind of operation, right? Any kind of operation, we actually need some operands. For example, if you want to add two numbers, right? Add, then we have one number, comma, another number. So these two numbers, right? We are adding it and save it to somewhere else. So how do you get these two numbers, right? Because these numbers is stored somewhere else, right? Either in the register or in the memory or in the input output, or maybe inside the code. So depends on the location of that operands. By the way, they called operands. So depends on the location of the operands. We actually have 4 different types of location. Okay, as you can see, location number 1 is the register, internal register of the processor, and we know that each processor, microprocessor, has its internal register, and in that internal register can store the data. All right. So this is the first location. That means where we can save our operands for calculation purpose. So this is the first location. Second location is inside the code. That means we actually can pass the data or store the data inside the code. So that is another location. Third location is most common one, is our main memory. We can store our operands, the value of the operands, into the main memory. So this is the third option, and maybe another option is the input output. So this is the four possible location. Okay, so based on this, we actually call them addressing mode. So we have four different types of addressing mode, right? First one, as we know, register addressing mode, where actually we store the data. That means that's why it's called register addressing mode. Second one, we call it immediate addressing mode. That means we store our data or pass our data inside the code. Third and fourth type is actually called the memory location. That means first one is the direct addressing mode, and the fourth one is the indirect addressing mode. Direct and indirect addressing mode is actually using our main memory. Okay, direct addressing mode and indirect addressing mode uses our main memory, because they store that variable or that operands or the value of the operands into our main memory. Okay, direct addressing mode and indirect addressing mode. While the other two, that means the first two one, that register and immediate addressing mode, register store the variable data into the internal register of the processor, and immediate addressing mode is we pass the information or pass the data through the whenever we write the code, we actually pass the data through that code. That is called immediate addressing mode. And we know that register is the fastest memory in our computer system. That's why register addressing mode is actually more efficient compared to the immediate addressing mode. Also, no, immediate addressing mode is also very efficient, but compared to the direct addressing mode and indirect addressing mode, because direct addressing mode and indirect addressing mode, they require memory access, main memory, which is slower, very slower compared to the register. So if you want to get the data from the main memory, you will actually need to access the memory. So you have to go to the access to the memory, you need to know the location of the memory, then you fetch the data and then come back to the processor, and then you can process the data. That means it takes longer time compared to the register addressing mode and compared to the immediate addressing mode, because for the register addressing mode you don't need to go to the main memory to fetch the data, because data is already inside the processor register, internal register, so you don't need to go to the main memory, and register is very fast. That's why they say that register addressing mode is the most efficient way of specifying data. Okay, immediate addressing mode is also better, as I said, because it's inside the code. Also, you don't need to go to anywhere. You just need to take care about the one register, because another data will already give it to you. Okay, so this is also good. Okay, so we will discuss one by one. So we let's start with the register addressing mode, which is not that much difficult. As you can see that this is an example. Let's say we have two register, EAX and EBX. By the way, do you remember what is EAX and EBX?
Yes, sir. Data register.
Yes, these are the data register, first data register. Yes, these are the two data register, EAX and EBX. So let's consider that we have this data register, and we want to move the data from EBX to EAX. All right. So for having the data of EBX or EAX, or was to storing the data from EBX and EAX, you actually don't need to go to anywhere else, right? Because it's inside the processor and it is faster. Okay, so very simple. So if you want to move, by the way, we know already what is the general format of the move. It is very simple, source to destination. That means the data of the source will go to the destination. That means data of EBX will actually move to the EAX location. So all of the operation related to this register is very, very simple and faster. Okay, as I said, that it is very easier to get the data and to store the data because it is inside the processor. You don't need to go to the main memory and then do all the operations. So this way, this register addressing mode is faster, and of course, it is efficient. Very simple, I think. So if you just read it, I hope you'll understand. Immediate addressing mode is also very simple. Look at the equation. I mean the example where we do the same types of operation, which is called move. Okay, in this move operation, we have, as you can see, we are moving this value this value into this register, AL register. And if you can remember EAX, I hope you also can remember AL. That is the lower part of the 8-bit register. So we are going to save 7 and 5 into the AL register. By the way, this is hexadecimal value. So you actually can save it into the 8-bit register. Okay. So for the data of this second value, that means the source, again, you don't need to go to anywhere else because it's inside the code. That's why it's very faster. Okay, it's also very efficient for doing any kind of assembly language instruction. So as we know, that immediate addressing mode and the register addressing mode are very simple to do and also very efficient. But the problem is you have very limited amount of register space. You might thinking that if it is very good, I mean, if it is very efficient for the register and immediate, then why we are going to use this slow direct addressing mode? The answer is we have very limited resource. Whenever you have hundreds of applications running at the same time, and everyone is trying to use the register itself in the processor register is not that much big, right? Only some megabyte. Okay, but you have hundreds of applications running at the same time. Everyone is actually wants to access the register, so it is not possible to accommodate all of them, right? That's why we have to use another addressing mode. That's why we have to store our data into the other memory location. In this case, is our main memory. Okay, so that's why we need these other two for our very limited resource. So I hope you understand these two, register and immediate. So let's come back to, because first two are very simple to understand, but the main problem is this one, direct addressing mode. Not problem, I mean a little bit complex. Direct addressing mode and indirect addressing mode. Okay, so direct addressing mode is, we know that it will need the memory access. So let's say, for example, in this case, we need two information. Okay, one is the, if you remember in the protected real mode memory architecture, chapter number 3, real mode memory architecture, we have discussed about the two things we needed for our logical memory address. Can you remember these two things? Exactly, it is the segment and it is the offset value. That means the base address of that memory segment. That means the starting point of that memory segment. Another value is the offset. That means how long is your data is, where by which you actually can find out your desired data from the memory. So here in direct addressing mode, we also do the same. We actually using that offset value so that we can find the data very easily. Okay, because you have to access the memory and find the data and fetch the data and do all the operation. Okay, so we remember, we in this direct addressing mode, we going to use that offset value. Sometimes they call it, as you can see, effective address. You just remember the offset value. Offset value is fine. Okay, and another important thing is this offset value is actually integrated with the code. That means whenever you define your variable, right, the assembler actually integrated those offset value into your code. And also we have the assembler will also use another thing which is called symbol table. I think you remember we have just discussed about the symbol table, that whenever you define this kind of data into the assembly language, the assembler is actually making a table, right? So here we also use, in direct addressing mode, we also use that symbol table with that offset value, which is integrated with the, which is integrated or attached with the code itself, so that we can find easily from the memory location. Okay, and let's have some example. There are something we actually need to see from here. So let's have some example. Look at this. This is our normal I mean definition, right? We define the data. One variable is response, another one is table one, another one is name one. All right. So that's the two things we have. There's the three variable we have discussed. Defined. So we can see that response variable is 1 byte. That means it's allocated 1 byte of data into the memory, and then the table variable is an array, right? Because it's writing times. So we have 20 elements. Each of the element is double word. That means we have 4 bytes for each element, right? And we have 20 data. That means 20 times 4, 80. That means they have allocated 80 bytes of data, okay, into the main memory. And we write the symbol table with the help of the offset value, and write the symbol table, right? And then we have another value which is called name one. Again, it's a byte type, but it is a multiple definition, because we have an inverted comma, and within this inverted comma we can see that we have written JIM space RAY. That means we have 3, 4, 5, 6, 7 character inside this. That means each of them, as I told you, each of the character require 1 byte of memory location. That's why altogether we have 7 byte of memory location in the memory. Okay, so that is our initialization. So after that, let's say we want to move the value of response, because the value of response is initialized by y. We want to move this value into AL register by using direct addressing mode. How we can do that? Okay, this is the code that move, this is the destination, comma, and this is the source. Look how they write the source. Why everyone's calling me now? So everyone is this is the write the code, this is the way we write the code. Look, this is the source. We actually moving the value of y. What is the variable name? Response. So we write response with the third bracket. Please remember, with this, whenever you write this kind of code in a direct addressing mode, if you want to use the value of any variable, all right, any value of any variable, you have to put a third bracket. Okay, you have to put a third bracket. That means the value of response variable. Okay, what is the difference? The difference is, if you don't put the third bracket, that actually means that it is the address of that variable. Let's say, for example, here, if you write in this way, in this direct addressing mode, that means table one and EBX, that means move. This is the destination, this is the source, and you think that the value of table one will go to the EBX. It's not like that in direct addressing mode. It's actually like that is if you don't write the third bracket, that means the address of table one will be moved to the value of EBX, to the EBX address. Okay, so if you want to use the value of any variable, you have to put that bracket. That means now it is fine that you have that bracket. That means the value of table will now go to the EBX register. So please remember this one also. Okay, so let's have the explanation. That means the first explanation, we can see this is the register. We move the value of response variable by using the third bracket, and then put it into the L register. Very simple. We can also do the things the same thing. We are putting the value of n into the value of response. So value of response, all right, not the address of the response. Again, move value of k will be copied or moved into the name variable, name one variable. Remember, name one has 7 bytes. So where you are going to put it, it's actually always you can put it in the first position. Okay, you cannot go to the another position. That is the disadvantage of this direct addressing mode. The disadvantage of direct addressing mode is you can only access in the first position of an array or of a multiple definition, because by using the direct addressing mode, you cannot access to the rest of the element. For example, last one. Look, it says that move table 1, the value of table 1 with the bracket 56, 5 and 6 actually, 5 and 6, so that is the value. It will go to the table 1 location, but the problem is it will only save into the first location of the table 1, because table 1 has, look at here, table 1 has 20 value, and it can access only the first element. And if you convert this data into our C code, this is our C code. Table 0, table 1, 0 equal to 56. I think the first position of that array actually now is now 56. Same as here. The first character of name 1 will be now K. Instead of J, now it is now K. That means it will be Kim Ray instead of Jim Ray. That is, the problem is that we cannot use, or we cannot access to the rest of the location of any multiple definition variable or into the array. That is the problem. Okay, but the good thing is we actually can use our memory location instead of the register, because the register is very short one. Instead of that, we can use our memory location by using by integrating the offset value with the help of the symbol table. Okay, so that is actually direct addressing mode. All right, but we have some problem anyway. So as we have just discussed that we have some problem in direct addressing mode. Okay, we have some problem in direct addressing mode because we cannot access more than one variable or more than one value, because we just can access the first location. We cannot access to the next location. So to solve this problem, that means to solve the to access to the other location of that array by using the assembly language, we can use indirect addressing mode. Okay, so let me show you by using the whiteboard or the paint. So in this addressing mode, what actually they have done is to solve the problem that we cannot access the second, third, fourth, fifth position or the other position of the array. We can only access the first position of the array. To solve the problem, we actually use another extra register to store the data, or to store the first or starting address of that table. Let me show you. Let's say, for example, in this direct addressing mode, what they have done is they have, let's say, for example, this is our array. Let's say this is our array. Okay, this is our array, and we have how many? Let's say 20, right? We have 20 value here. One, let's say it's very 1, 2, 3, 4, something like that. Okay, let's say this is position number 0, that is 1, that is, sorry, 2, 3, let's say this is 19. Sorry, my mouse writing is not horrible actually. Anyway, so so let's say this is our array. Okay, this is table 1, this is array, and we need to store the data in each position. In direct addressing mode, we cannot do that because we can only access to the first position. We cannot access to second, third, fourth, fifth, and other position. To solve the problem, we have indirect addressing mode. So to solve the problem, indirect addressing mode is actually using another register here to store the first location of the data. This is the initial value, right? So this is the initial address. Okay, so we have another register. Let's say the name of the register is EBX or EAX. Let's say it's EAX. Let's say EAX. So let's say this is our EAX register, right? We need to use this EAX register to store, first of all, to store the location or the address of this array. So what is the technique is? Technique is, first of all, we need to store the first initial address of this array, right? First initial address. Let's say the address is, let's say for example, 1100. That is our initial address of this array. So that means we know the first location. Okay, so it's very simple. If we know the location, if you know the location is very simple, we can put the data. For example, here we copy the first, we copy the address of the table 1. Remember, this is without third bracket. That means this is not the value, this is actually location or address of table 1. Now will be in EBX. Here the location of address, first address of array, now is copied into the EAX register, right? That is the first line of code. Second line of code, we are moving the value of 100 into the value of EBX. All right, that means EBX is actually, this is actually not, this is EBX. EBX is now without the third bracket is actually a location. With the third bracket is actually the location of the value, location of that table 1. Okay, that means now we store value 100 into the location of EBX, which is here. Let's say for example this is 100 now. Fine, very simple. So we load the initial address, that is the first address, into this register, and then using that register we save the value of 100 into this first point, first value. But the problem is we cannot, how do you know that what is the second position? How do you know that what is the second position? If we cannot find the second position, that means the address of the second position, we actually cannot load the data because it is only the first location. That means if you cannot change this value, according to the second location, we actually cannot put the value. So how we can find this location? Okay, the clue is, yeah, so look at it. Whenever we initialize the value, if you remember how we initialize the value here, each of the value of table 1 is actually, right, DD type. DD means double word. Double word means 4 byte. That means each of the table 1 value occupy 4 byte of data into the memory, right? Into the memory. That means first value of table 1 occupy 4 byte, right? Second value will occupy next 4 byte. Third value of table 1 will be the other 4 byte. So we know this value. So if we can use this offset value of 4, and then we can easily calculate that, yes, if we know the first location, and if you know the offset value, if you add it together, it will be very easy that we can find the next location. That's why, look at the indirect addressing mode. What actually they have done is they have add without the third bracket of EBX. That means that is the address, this one, 1100. Okay, 1100 comma 4. We have added the value of this address, which is the initial address here, right? Initial address of this 1100. We have added this value plus offset value of 4. Why? Because the each value of this array is actually 4 byte. So to find the next location, we just added 4 here. That's why they have add the address of the EBX and add 4. That means EBX equal to EBX plus 4. Now we know that, yes, now this is 110. Let's say, for example, 4. Now this is 1104. And 1104 is the address of the second position of that array. And now it is very easy to copy the data, right? To move the data. Now we are moving the value of 99 into the, see, with the third bracket. That means now it's going to the value of EBX. That's why now it is now second position is now 99. Okay, the same way you can access all of the array in the memory location, because now we know that, yes, if you add 4444, you actually can easily find the location first, and then you can put the value. So if I ask you that put the value of 1000 into the let's say seven position of that array. So it's very easy. You have to count that. Okay, this is 1, 2, 3, 4, 5, 6, 7. What will be the 7 position? And then add it 4, 4, 4, 4, 4, and then it will be the 7 position. After finding the 7 position, you have to update the EAX, and then you can easily put the value into the 7 position of that array. So that is the technique used in indirect addressing mode, so that we can access the value of each location. All right.